Welcome to the deep dive. Today we're going into the really fascinating capabilities of CNC turn mill machines.
That's right.
If you've ever been curious about how those incredibly complex metal parts get made, the kind you find in, say, advanced aircraft engines or really precise medical implants, like you're definitely in the right place.
hmm
We've pulled together some really insightful material to explain what exactly makes these machines so much more advanced than, well, your standard CNC lathe.
Absolutely.
Hmm.
And the core problem, really, that turn mills solve is inefficiency and also the potential for inaccuracies that pop up when you have to move a part between different
Right, like
machines.
from a lathe to a milling machine.
Exactly. Using a lathe for the round bits, then a separate mill for, I don't know, flats or holes. Think about the wasted time just moving it, the extra handling,
And the errors.
and the errors, yes.
Yeah.
Every single time you unclamp and reclamp that part, you're
Wow.
introducing a tiny bit of potential error. It adds up.
Okay, so let's unpack this. Our mission for this deep dive is to really get under the hood, understand what gives these turn mill machines their edge. We're going to look at key technologies,
Well,
things like live tooling,
crucial stuff.
the very important y-axis, and this whole concept of done-in-one machining.
Yeah, and that done-in-one idea, it's critical.
Right.
Keeping the part clamped isn't just faster.
No.
No, it fundamentally cuts out those compounding errors you get from multiple setups. It's about precision as much as speed.
Makes sense. So ready to jump in?
Definitely. Let's start with the basic difference. What makes a turn mill not just a regular CNC lathe?
Good question. So a standard CNC lathe, its whole purpose is creating cylindrical shapes, right?
Right.
It spins the workpiece, and stationary cutting tools come in and shape it. Simple enough. But what if you need features that aren't round?
Like a flat side or maybe a bolt pattern?
Exactly. Or hole drilled into the side. That's where a standard lathe kind of hits its limits. Now, a turn mill,
Yeah.
it's more like a hybrid.
Hybrid is a great word for it. It does everything a standard lathe can do, sure. But critically, it can also spin the cutting tools themselves,
While the workpiece is held still.
held still, or maybe indexed to a specific angle. So it's like having, well, both a lathe and a milling machine rolled into one single unit.
Okay, so that analogy you mentioned. A regular lathe is like a potter's wheel, spinning clay, fixed tools shaping it.
Yeah, basically. A turn mill is like that, but now some of your shaping tools can also spin and move around the clay even if the wheel is stopped or just stepping between positions. Like, think clock hands ticking.
Gotcha. And that integration, that combination of turning and milling in one machine, that's where the big efficiency boost comes from.
Absolutely. No more shuttling parts back and forth.
Yeah.
And as our sources really emphasize, this is becoming super important in industries like aerospace, automotive,
Medical devices, too, you mentioned.
especially medical. They need incredibly complex parts, and the precision has to be spot on. Turn mills deliver that.
Okay, so integration is key. And you said the technology that really enables this is live tooling.
Exactly. Live tooling. It's the game changer, really. It sounds simple, but it fundamentally alters what the machine can actually do.
All right, live tooling, break that down for us. What does it mean?
Okay, so think of the turret on a lathe, that big disc that holds all the cutting tools. On a turn mill, some of those tool stations on the turret are powered. They can hold rotating cutting tools like end mills, drills, taps.
The kind of tools you'd normally use on a milling machine.
Precisely. So while your main spindle is holding the workpiece nice and secure, these powered spinning tools can come in and perform milling, drilling, tapping operations right there.
So the tool spins, not just the part.
That's the core insight, yes.
Yeah.
You shift from only having fixed tools shaping a spinning part to also having powered spinning tools that can shape a stationary or indexed part. It brings milling flexibility onto the lathe platform.
Which is a massive leap from a standard lathe turret, which just holds static, non-spinning tools.
A huge leap. On a regular lathe, it's just fixed tools. But with live tooling, specific spots on the turret have their own little motors.
Dedicated motor.
Dedicated motors, yes, spinning the cutting tool in special holders. And here's a key detail. While that live tool is working, the main spindle holding the part can either rotate to position it precisely, that's your C-axis control.
Like rotating it to present a different face.
Exactly. Or it can just stay completely still.
So suddenly you're doing jobs that were just impossible on a lathe before. Like what specifically?
Oh, loads of things. Think about milling a perfect flat onto a round shaft, or drilling holes clean through the side of the part cross holes, we call them.
Okay.
Or even tapping threads into the side of a cylinder. You could etch patterns, complex shapes, all on what's basically a lathe. The versatility is pretty impressive.
And the efficiency impact. I mean, it must be huge. You're cutting out entire machine transfers.
Exactly. Performing these milling and drilling ops in the same setup as the turning. It just slashes the total production time.
And less handling means less risk too, right?
Absolutely. Less manual handling, less chance of dropping or damaging the part, moving it between machines. It just smooths out the whole workflow.
Okay, now earlier you touched on accuracy. It feels intuitive that fewer setups means better accuracy, but let's dig into that. This done-in-one machining idea, how did it really boost precision on a turn mill?
Right. This is so, so important. Every time you move a part between machines.
Unclamp, move,
Yeah.
reclamp.
You're basically giving errors a chance to sneak in. Tiny little positioning errors, maybe a bit of dirt under the clamp.
Doesn't sound like much.
Individually, no. But for complex parts needing tight tolerances between features, these tiny errors accumulate. They stack up. And suddenly your part might be scrap.
Okay, so how does doing it all in one go on the turn mill fix that?
Well, done in one fundamentally improves accuracy because it prevents that error accumulation. The part stays locked in the same spindle for all the turning, milling, drilling, whatever it needs.
So you're not constantly trying to find your starting point again on a different machine.
Exactly. You eliminate the inconsistencies that come from reestablishing your reference points, your datums. You set your zero once, and everything is machined relative to that single consistent origin.
One setup, one set of references. Makes total sense. Can you break down the specific benefits of clamping it just once?
Sure. First, like we said, you basically eliminate reclamping errors. Every fixturing has tiny potential variations. Multiple setups multiply that risk. Single clamping, just one potential instance.
Okay.
Second, you get that consistent datum reference. All features are machined relative to the same starting point. Move the part, establish a new datum. You get tiny datum shift, we call it. That kills positional accuracy between features done in different setups.
So it keeps everything perfectly aligned to the original plan.
Perfectly aligned, yes. And that helps maintain crucial geometric relationships, like how concentric is this bore to that outer diameter? How perpendicular is this milled face to that turned shoulder? How parallel are these two flats?
Much easier to control when it hasn't moved.
Much easier. Plus, less handling means less chance of introducing stresses or tiny distortions, especially in maybe less rigid materials. One clamping minimizes that risk, so you get better dimensional stability.
Wow. Any other benefits?
Well, maybe a bit subtler. But machining all surfaces on one machine, often under similar conditions, can lead to a more consistent surface finish across the whole part.
That's quite a list. And you mentioned things like aerospace turbine blades, medical implants, parts where tiny errors are just not acceptable.
Absolutely. For those high-consequence parts, the precision you get from done-in-one on a turn mill isn't just nice to have, it's often mandatory.
All right, let's shift gears a bit. Another key capability you brought up is the y-axis. Now, on a standard lathe, you've mostly got x-axis for diameter and z-axis for length. What does adding this y bring to the party?
That's right. Without a y-axis, if you need a feature that's not right on the center line of the part, say a keyway milled into the side, or maybe some holes offset from the middle.
How would you even do that?
Well, you typically have to rely on the c-axis, the spindle rotation, combined with x and z moves. It's called interpolation, using coordinated moves of the axis you do have to sort of fake the movement you need.
Sounds complicated. And maybe not that accurate.
It can work for simpler things, but yeah, it can be limiting and often less precise for true off-center milling. The y-axis gives you that missing linear movement.
So the y-axis, what is it exactly? How does it move?
It's a linear axis, usually perpendicular to both x diameter and z length. Imagine the cutting tool being able to move straight up and down, or maybe straight forward and back, relative to the exact center of the spindle holding the part.
Ah, okay. Like a direct sideways movement for the tool.
Exactly. It provides what's called transverse feed.
So instead of just rotating the part to get to an off-center spot, the tool itself can just drive straight there. What does that capability unlock?
This is where the y-axis really shines. It's essential for accurately machining features that don't sit on the rotational axis. We're talking milling precise keyways, creating flats on shafts that are offset from the center, machining complex pockets, maybe drilling accurate bolt patterns that aren't just in a simple circle around the middle.
It really sounds like it just blows open the possibilities for part geometry.
It absolutely does. When you coordinate that y-axis movement with x, z, and c, and maybe even a b-axis on fancier machines, which lets the tool tilt.
A tilting tool. Wow.
You can create much more complex, intricate surface contours and features. Super important in automotive, medical, aerospace, anywhere you have parts with specific, often non-symmetrical shapes.
You mentioned different types of y-axis briefly.
Yes, some machines have a real y-axis, a dedicated mechanical slide for direct linear motion. Others might use a virtual or interpolated y, where that y motion is achieved by coordinating other axes, often x and c.
Does one work better than the other?
They have different design trade-offs, maybe affecting rigidity or machine footprint. But the core benefit, that ability to move the tool linearly off the spindle center line, that's the key takeaway. Adding a y-axis really transforms the turn mill into a true multitasking machine.
It's definitely clear these machines are way beyond just basic turning plus a bit of milling. What other really complex stuff can they handle? Feels like maybe we underestimate them.
I think people often do, yeah. They might think, oh, it's a lathe that can mill a flat. But modern turn mills, they can tackle an incredibly wide range of complex ops things that used to need several different specialized machines.
Okay, lay some on us. What kind of advanced operations?
All right, well, think about multi-axis contouring, moving in X, Y, Z, C, maybe B, all at the same time to create really complex 3D shapes.
Like sculpting.
Kind of, yeah. Then there's angled drilling and milling using that B-axis tilt to get the tool approaching the part from different angles. They can even do things like gear cutting.
Really? Cutting gears on a lathe?
On a turn mill, yes. Hobbing or shaping sometimes.
Yeah.
Deep hole drilling for specific needs. Super precise boring for internal diameters. Even secondary things like knurling for grip surfaces or complex grooving. And the kicker is often all in that first clamping.
That list is seriously impressive. How do they manage all that complexity? The control system must be pretty advanced.
Oh, definitely. It's a combination of things. That live tooling we talked about, the y-axis, often a b-axis tilt, and incredibly sophisticated CNC controls that can choreograph all those simultaneous movements precisely. They generate really complex tool paths to machine these intricate features.
And you mentioned simultaneous machining earlier, too.
Yeah, on some high-end machines, you can literally have, say, a turning tool working on one feature while a live milling tool is working on another feature at the same time.
On the same part.
On the same part. It just crushes cycle times, boosts productivity even more. For those complex, high-value parts, this level of integration makes turn mills incredibly productive and ultimately cost-effective despite the initial investment.
Well, this has been a really eye-opening deep dive into CNC turn mills. It's crystal clear they offer huge advantages over standard lathes when you need to make complex parts.
Absolutely. That integration of live tooling, often plus the y-axis, lets them perform turning, milling, drilling, and, a whole host of other advanced operations, all in one go.
All in that single clamping.
Which, as we discussed, massively improves accuracy, slashes setup time, and just makes the whole manufacturing process way more efficient.
And for you listening in, we really hope this discussion has given you a quick but pretty thorough understanding of this key manufacturing technology, a bit of a shortcut to getting up to speed.
Indeed. And it leaves us with a thought maybe for you to mull over. As we see more and more machining capabilities getting packed into single machines like these turn mills, how is that trend going to keep reshaping manufacturing?
Yeah, what's next?
What future innovations might blur the lines even further between, what we traditionally think of as a lathe, maybe even other processes? It's definitely something to consider, both for how products get designed and how we actually make them going forward.